Welcome to today's session. In this video, we will be diving into problem number 213, House Robber 2. This is a classic dynamic programming problem that builds on the concepts of the original House Robber problem, but with a twist. This time, the houses are arranged in a circle. We'll explore how to approach this problem effectively, discuss its challenges, and implement an optimal solution. Let's get started. In this problem, you are a professional robber planning to steal money from houses arranged in a circle. Each house has a certain amount of money stored, but there's a catch: you cannot rob two adjacent houses on the same night, as it would alert the police. Since the houses form a circular arrangement, the first house is also a neighbor of the last house, making the problem slightly more complex. The goal here is to determine the maximum amount of money you can rob without triggering the alarm. You are given an integer array called nums, where each element represents the money stashed in a house. The output will be a single integer, which is the maximum money you can rob while following the rules. For example, consider an input array nums equals 2, 3, 2. In this case, the optimal strategy is to rob house 2, which contains 3 units of money. If you attempted to rob house 1 and house 3 instead, it would alert the police because these houses are adjacent in a circular arrangement. Therefore, the maximum money you can rob is 3. Another example is nums equals 1, 2, 3, 1. Here, the best approach is to rob house 1, which contains 1 unit, and house 3, which contains 3 units. This combination avoids robbing adjacent houses and gives a total of 4. Notice that you cannot rob house 4 because it is adjacent to house 1. Now, let's look at another example where nums equals 1, 2, 3. In this case, you can either rob house 2, which contains 2 units, or house 3, which contains 3 units. Robbing house 1 along with house 3 would trigger the alarm since they are adjacent in the circular layout. The maximum money you can rob here is 3. The problem also comes with constraints. The array length will range from 1 to 100, and each house's money value will be between 0 and 1000. This ensures the input is manageable but requires an efficient solution to handle edge cases and larger inputs. Finally, let's discuss some edge cases. If the input array contains only one house, such as nums equals 10, the result is simply the value of that house, which is 10. Another edge case is when all houses have 0 money, like nums equals 0, 0, 0. In this scenario, the output is 0 since there's nothing to rob. When there are exactly 2 houses, you should rob the house with the larger value. For example, if nums equals 5, 10, the result is 10. Lastly, the solution must handle large inputs efficiently, such as arrays of length 100 with values up to 1000, ensuring that it performs well under these constraints. To solve the House Robber 2 problem, we first consider a brute force approach. The main challenge arises from the circular arrangement of the houses, which means the first and last houses cannot be robbed together. A recursive solution could explore all possible combinations of robbing or skipping houses, but it must ensure that this circular condition is respected. Specifically, we evaluate 2 cases: robbing houses from index 0 to n2, which excludes the last house, and robbing houses from index 1 to n1, which excludes the first house. However, this approach is highly inefficient because the recursion results in an exponential time complexity of O2 to the power of n. The repeated calculations for overlapping subproblems make this method impractical for larger inputs, as it quickly becomes too slow to handle competitive programming scenarios or real-world applications effectively. To overcome the inefficiencies of the brute force method, we use dynamic programming, which optimizes the problem by breaking it into 2 linear subproblems. The key idea is to treat the circular problem as 2 independent instances of the simpler house robber I problem. For each instance, we compute the maximum sum for the 2 ranges, houses 0 to n2 and houses 1 to n1, using a recurrence relation. Here, we define a DP array, where DP, I, represents the maximum sum obtainable up to house I. The relation DP, I, equals max, DP, I1, nums, I, plus DP, I2, ensures we either skip the current house or rob it while avoiding adjacent robberies. We then compute the results for both ranges and return the maximum. This approach has a time complexity of O(n), as each range is traversed once, and a space complexity of O(n) for the DP array. However, it's worth noting that this space complexity can be further reduced by realizing we only need the last two states of the DP array at any given time. This leads to an optimized version that uses constant space. The optimized dynamic programming approach is the natural choice for this problem. It builds on the efficiency of the standard DP method while significantly reducing space usage. Instead of maintaining an entire DP array, we use two variables, previous 1 and previous 2, to store the last two states. This drastically reduces the space complexity from O(n) to O(1). For implementation, we initialize these two variables and iterate through the houses, updating them at each step to calculate the maximum sum for both ranges. After computing the results for the two ranges, we return the maximum of the two. This approach is ideal because it balances time and space efficiency, making it suitable for both competitive programming and practical applications. The main insights that lead to this solution include recognizing that the circular constraint can be broken into two linear subproblems and applying the recurrence relation from house robber I. While the space optimization slightly impacts code readability, the trade-off is minimal compared to the performance benefits. In conclusion, the optimized dynamic programming approach is the best strategy for solving the house robber 2 problem. It effectively handles the circular constraint by splitting the problem into two linear subproblems and uses constant space to achieve optimal performance. This method strikes an excellent balance between efficiency and simplicity, making it both practical and elegant. By leveraging the recurrence relation from house robber I and focusing on the last two states at any time, we ensure the solution is not only fast but also memory efficient. This makes the optimized DP approach the clear winner for tackling this problem. In this problem, we're tackling a variation of the classic house robber problem, but with an added twist: the houses are arranged in a circular neighborhood. This means the first and last houses are neighbors, which complicates our decision-making, as robbing one affects the other. The goal remains the same: to rob the maximum amount of money without alerting the police, which means we cannot rob two adjacent houses. To approach this, we first need to understand the problem constraints. The circular layout means the first and last houses are directly connected, so we can't simply treat the array as linear. To simplify, we break this into two separate cases, one where we exclude the first house, and another where we exclude the last house. By solving these two linear subproblems independently and taking the maximum of the results, we can effectively handle the circular constraint. Now, let's define the subproblem for the linear version of the house robber problem. Dynamic programming is the key here. We define DP, I, as the maximum amount of money that can be robbed from the first I houses. To decide whether to rob the ith house, we have two choices: either rob it, which forces us to skip the I1th house, or skip it and take the result from the I1th house. This gives us the relation dp I equals max nums I plus dp I2 dp I1. For the base cases, if there's only one house, dp 0 equals nums 0, and if there are two houses, dp 1 equals max nums 0 nums 1. Once the linear version is defined, we solve the two cases for the circular problem. In the first case, we exclude the first house and consider the array from index 1 to n1. In the second case, we exclude the last house and consider the array from index 0 to n2. The result is simply the maximum value obtained from these two cases. Edge cases also need to be addressed to ensure our solution is robust. If there's only one house, the solution is straightforward: just return its value, since there are no other options. If there are two houses, we simply return the maximum of the two, as robbing one excludes the other. A key insight is that the circular constraint can always be reduced to two linear subproblems by excluding either the first or the last house. Dynamic programming is well suited for this problem because it has overlapping subproblems and an optimal substructure. Moreover, since the decision at each house only depends on the previous two states, we can optimize space usage. Instead of maintaining an entire DP array, we only need two variables to represent the last two states. This significantly reduces the space complexity while maintaining the same efficiency. To optimize our algorithm further, we use a space-efficient dynamic programming approach. We define a helper function rob_linear nums to handle the linear version of the problem. In this function, we initialize two variables, previous 2 for the result 2 houses back, and previous 1 for the result 1 house back. As we iterate through the houses, we calculate the maximum money that can be robbed at the current house using the relation current equals max, nums, I, plus previous 2, previous 1. We then update previous 2 to previous 1 and previous 1 to current, effectively rolling our two variables forward. At the end of the iteration, previous 1 holds the maximum money robbed. For the circular problem, we solve it by calling rob_linear twice, once excluding the first house and once excluding the last house. The final result is the maximum of these two cases, giving us the optimal solution while using only O1 space. Let's go through an example to see the algorithm in action. Consider the array nums equals 2, 3, 2. First, for the case where we exclude the first house, the subarray becomes nums1 equals 3, 2. Using the rob_linear function, we find the maximum money is max, 3, 2, equals 3. For the second case, where we exclude the last house, the subarray is nums2 equals 2, 3. Again, applying rob_linear, the result is max, 3, 2, equals 3. The overall maximum is max, 3, 3, equals 3. From this, we conclude that the maximum amount of money we can rob is 3. In terms of complexity, this algorithm runs in O(n) time, as we process each house once for each of the two cases. The space complexity is O(1), as we use only two variables to store intermediate results, making it both efficient and scalable. This Python implementation solves the house robber 2 problem effectively by leveraging a helper function and considering the problem's circular constraint. The key idea is to break the circular dependency by treating the problem as two independent linear problems, one excluding the first house and the other excluding the last house. First, the rob function handles edge cases. If the input list nums is empty, it returns 0 since there are no houses to rob. If there's only one house, it directly returns the amount in that house. These edge cases ensure the solution handles small inputs gracefully. Next, the helper function rob_linear calculates the maximum amount that can be robbed from a linear sequence of houses. It uses two variables, prev_max and cur_max, to keep track of the maximum amounts robbed so far without using extra space for a DP array. For each house, the algorithm decides whether to include it in the robbery, by adding its value to prev_max, or skip it, keeping cur_max unchanged. This ensures the solution runs in O(n) time with O1 space. Finally, the solution calculates the maximum amount that can be robbed by comparing two scenarios, robbing all houses except the first, nums1, and robbing all houses except the last, nums:1. The maximum of these two scenarios is returned as the result. This approach ensures the circular dependency is resolved while maintaining the constraints of the problem. The implementation is efficient, clean, and handles all edge cases, making it suitable for a production environment and competitive programming contexts. This is the Java implementation of the house robber 2 problem, number 213. The logic mirrors the Python solution, using a helper method to handle the linear house robber scenario for two subsets of the array, one excluding the first house and the other excluding the last house. Key differences include the use of Java's built-in arrays.copy of range for slicing and explicit type declarations. The implementation handles edge cases like empty arrays and single-element arrays effectively. To solve the problem of robbing houses arranged in a circle, we need to account for the fact that the first and last houses are adjacent. This means we cannot rob both of them, so we divide the problem into two scenarios. First, we consider robbing houses excluding the first house, which leaves us with the sequence 3, 2. Second, we consider robbing houses excluding the last house, resulting in the sequence 2, 3. By solving these two subproblems individually and taking the maximum of the two results, we ensure no adjacent houses are robbed while maximizing the total amount. Now, for the first scenario with 3, 2, we use the helper function rob_linear. Initially, both prev_max and cur_max are set to 0. At the first step, we encounter the house with 3. The current maximum becomes the higher of the previous maximum or the sum of the previous maximum plus the current house value, which is max, 0, 0 plus 3, resulting in 3. We then update prev_max to the previous value of cur_max, which remains 0. At the second step, the house has 2. Again, we calculate cur_max as max, 3, 0 plus 2, which remains 3, and update prev_max to 3. This gives us a result of 3 for robbing the sequence, 3, 2. The result of robbing the sequence, 3, 2, is 3. Now, we move on to the second scenario, where we exclude the last house and compute rob_linear for the sequence, 2, 3. Again, we start with prev_max and cur_max both set to 0. At the first step, the house value is 2. The current maximum becomes max, 0, 0 plus 2, which is 2, and we update prev_max to 0. At the second step, the house value is 3. We calculate the current maximum as max, 2, 0 plus 3, which is 3, and update prev_max to 2. The result for this sequence is also 3. Finally, to determine the overall maximum amount we can rob, we take max, 3, 3, which gives us 3. Therefore, the output for this example is 3. For the second example, where the input sequence is 1, 2, 3, 1, we follow the same logic. First, we exclude the first house and consider the sequence 2, 3, 1. Then, we exclude the last house and consider the sequence 1, 2, 3. Using rob_linear on 2, 3, 1, we start with prev_max and cur_max both set to 0. For the first house, which has a value of 2, the current maximum becomes max, 0, 0 plus 2, resulting in 2, and prev_max is updated to 0. For the second house with a value of 3, the current maximum becomes max, 2, 0 plus 3, which is 3, and prev_max is updated to 2. For the third house with a value of 1, the current maximum becomes max, 3, 2 plus 1, which remains 3, and prev_max is updated to 3. Thus, the result for robbing the sequence, 2, 3, 1, is 3. Next, we compute rob_linear for the sequence, 1, 2, 3. Starting with both prev_max and cur_max set to 0, we process the first house with a value of 1. The current maximum becomes max, 0, 0 plus 1, which is 1, and prev_max is updated to 0. For the second house with a value of 2, the current maximum becomes max, 1, 0 plus 2, resulting in 2, and prev_max is updated to 1. For the third house with a value of 3, the current maximum becomes max, 2, 1 plus 3, which is 4, and prev_max is updated to 2. The result for robbing the sequence, 1, 2, 3, is 4. Finally, we calculate the overall maximum by taking max, 3, 4, which gives us 4. Therefore, the output for this example is 4. In the final example, the input is 0, which means there is only one house with a value of 0. Since there are no other houses to consider, the maximum amount we can rob is simply the value of this single house, which is 0. Thus, the output for this example is 0. The time complexity of our solution can be analyzed by breaking it down into two parts, the helper function and the main function. First, in the helper function, rob_linear, we process the list of houses in a linear manner. This means we iterate through the houses array exactly once, performing simple operations like updating prev_max and cur_max for each house. As a result, the time complexity of rob_linear is O, k, where k is the length of the array passed to it. In the main rob function, we call rob_linear two times, first for the array excluding the last house, and then for the array excluding the first house. Since each of these arrays has a length of n1, where n is the length of the input nums, the total time complexity becomes O, n1, plus O, n1. Simplifying this gives us O, 2 asterisk, n1, which is equivalent to O, n, when we drop constants in big O notation. Now, let's examine the space complexity. The helper function, rob_linear, uses only two variables, prev_max and cur_max, to keep track of intermediate results as we iterate through the array. These variables require constant space, or O1. No additional data structures are used, and the function operates entirely in place. For the main function, there are also no additional memory allocations beyond the variables needed for intermediate calculations and the two calls to rob_linear. Since the solution doesn't use any data structures or recursive calls, the overall space complexity of the entire solution is O1. To put this solution into perspective, let's compare it with a naive approach. A brute force solution would involve recursively exploring all possible subsets of houses to rob, ensuring no adjacent houses are selected. This would lead to an exponential time complexity of 2 to the power of n, as there would be 2 to the power of n possible subsets. Clearly, this approach becomes computationally infeasible for even moderately large inputs. In contrast, our optimized dynamic programming approach simplifies the problem by breaking it into two linear subproblems, one for nums, :1, and another for nums, 1. This reduces the time complexity to n, which is significantly more efficient. Moreover, by using only two variables, prev_max and cur_max, instead of a full dynamic programming table, we reduce the space complexity from n to 1, making the solution both time and space efficient. Let's delve into the best, average, and worst-case scenarios for this solution. In the best-case scenario, the input array nums contains only one house. Here, the function directly returns the value of nums, 0, resulting in a time and space complexity of 1. For the average case, with a typical input array of length n, the function processes two subarrays of size n1, leading to a time complexity of n, and a space complexity of 1. Similarly, the worst-case scenario also involves an input array of length n, and the complexity remains n for time and 1 for space. Now, examining the mathematical proof for time complexity, each call to rob_linear involves iterating through an array of length n1, performing constant work for each iteration. Since rob_linear is called twice, the total time complexity becomes 2 *o n1, which simplifies to 2 n 2, and ultimately reduces to n, when constants are ignored in big O notation. Finally, let's validate the space complexity. The solution uses a constant amount of additional memory, specifically for variables like prev_max, cur_max, and a few temporary ones during execution. Since no additional arrays or recursive calls are made, the space usage remains constant at 1. In conclusion, this optimized dynamic programming solution achieves a time complexity of n, and a space complexity of 1, making it an extremely efficient approach for solving the house robber 2 problem. This balance of optimal time and space usage ensures the solution scales well even for large inputs. One of the most common mistakes in this problem is overlooking the circular constraint. Remember, the houses are arranged in a circle, meaning the first and last houses are neighbors. If you treat the problem as a simple linear sequence, you might accidentally include both the first and last houses in the solution, which violates this constraint. To handle this correctly, you need to evaluate two separate cases, one where you exclude the first house and another where you exclude the last house. Another frequent issue arises with base cases. For instance, when there's only one house, the solution is straightforward: the maximum loot is just the value of that house. Failing to account for such scenarios can lead to errors or even runtime crashes. Additionally, dynamic programming relies heavily on solving subproblems, and if you don't use memoization, the recursive solution can easily become inefficient, with exponential time complexity. Instead, always store the results of subproblems in a memoization table or use an iterative DP approach. Watch out for off-by-one errors as well. When splitting the array into two cases, ensure the indices are correctly defined. Misplacing a boundary can significantly impact the result. Lastly, consider space optimization. Many solutions use n space for DP arrays, but this can often be reduced to 1 by maintaining only the last two states of the computation. Now, in interviews, recognizing patterns is key. This problem is a variation of the simpler house robber problem, where the arrangement is linear. Identifying the circular constraint is critical because it changes how you approach the solution. By splitting the problem into two subproblems, one excluding the first house and the other excluding the last, you effectively handle the circular dependency. When explaining your approach to an interviewer, it's important to clearly articulate why this division is necessary and how it ensures the constraint is respected. Optimization is another valuable discussion point. For example, transitioning from an n space solution to 1 by using rolling variables demonstrates a strong understanding of space efficiency. Don't forget to explicitly address edge cases, such as when there's only one house or two houses, as this shows thoroughness in your thought process. Related problems can also come up during discussions. House Robber number 198 is the foundational version without the circular constraint, while House Robber 2 is the circular version we're tackling here. You might also draw connections to Paint House number 256, another DP problem with a different setup, or Maximum Subarray number 53, which shares similarities in optimizing subarray solutions using DP techniques. There are alternative approaches to solving this problem, though some are far less efficient. For instance, a brute force approach explores all possible subsets of houses while ensuring no two adjacent houses are robbed. While simple in concept, this method has an exponential time complexity of 2 to the power of n, making it impractical for larger inputs. In contrast, dynamic programming is the most efficient approach. By breaking the circular dependency into two linear cases, one excluding the first house and the other excluding the last, you can compute the maximum loot for each case in n time. The final result is simply the maximum of these two values. To further optimize space, the sliding window technique reduces the space complexity to 1 by maintaining only two variables for the previous states, rather than storing an entire DP array. Overall, the optimal solution achieves a time complexity of n and a space complexity of 1, making it both fast and memory efficient. Great job following along. Today, we tackled problem number 213, House Robber 2, and learned how to handle circular constraints in dynamic programming problems. We discussed the significance of breaking the problem into subproblems, optimizing for time and space, and considering edge cases. Thanks for watching, and I encourage you to keep practicing and exploring more dynamic programming problems. Don't forget to like, subscribe, and share your thoughts in the comments. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!